All right, today we are diving deep. We're going to crack open the atom itself to solve a genuine nuclear mystery. A case of some missing mass that, just happens to lead us straight to the most famous equation in all of science. And it all kicks off with a simple question of scale.
Okay, to really get our heads around the world we're about to step into, let's start with a classic analogy. I want you to picture an atom, the fundamental building block of literally everything, and imagine we could just blow it up until it fills an entire classroom.
So now you're standing in this giant classroom-size atom. Where's the nucleus? Well, it would be no bigger than the head of a pin. Seriously, just a tiny speck in the middle of the room. And the rest of that vast space, it's pretty much just empty space.
But here's where it gets really mind-bending. That tiny, tiny pinhead, it contains more than 99.9% of the atom's entire mass. I mean, all the stuff, all the weight, is just crammed into this unbelievably small space. So, what in the world is going on in there?
Well, to find out, we have to zoom way in on that pinhead. It's time to meet the residents of the nucleus and figure out what it's actually made of.
For all that density, what's inside the nucleus is actually pretty simple. You've really only got two types of particles, which we call nucleons. You've got your positively charged protons and your neutrons, which have no charge. They're almost the same mass, and it's the number of these little guys that basically defines what an element is.
But here's a cool little twist. The number of protons? That's fixed. That's what makes oxygen oxygen and not gold. But the number of neutrons, well, that can change. And when it does, you get different versions, or as scientists call them, isotopes, of the very same element.
Let's take hydrogen, for example. It's the simplest one out there. Regular old hydrogen is just a single proton. That's it. But if you add a neutron, bam, you get something called deuterium. Add another neutron and you get tritium. The important thing to remember is, chemically, it's all still hydrogen. It just has a different weight.
Okay, so now that we know the building blocks, we can finally get back to our central mystery. See, when physicists started doing the math, weighing the nucleus and then weighing all its individual parts separately, they found something really strange. Something that, it just didn't add up.
So let's play detective for a second. We'll use a common oxygen nucleus, oxygen-16, as our case file. The recipe is simple: 8 protons and 8 neutrons. We know exactly how much a single proton weighs and how much a single neutron weighs. So, logically, we should just be able to add them all up to get the total mass of the nucleus, right?
Wrong. Just look at these numbers. The expected mass, which you get when you add up all the parts, is actually more than the actual measured mass of the nucleus when it's all together. It's like the final product is somehow lighter than its ingredients. So, where did that mass go? It's like it just vanished.
And no, this isn't some kind of measurement error. It's a fundamental property of our universe. Scientists even gave this missing mass a name. They call it the mass defect. But, just naming something doesn't really explain it. To do that, we're going to need a little help from a certain genius.
Yeah, the solution to our little puzzle doesn't come from where you might expect. It comes from Albert Einstein and his groundbreaking theory of special relativity. And the whole idea is captured in just 3 letters and a number that completely changed the world.
E equals mc squared. I mean, you've seen it everywhere, right? On t-shirts and movies. But what does it actually mean? Well, think of it like a cosmic conversion formula. It's telling us that mass and energy aren't really separate things at all. They're just two sides of the same coin. Mass is basically just a super concentrated form of energy.
And that right there is the answer to our mystery. The mass wasn't lost. It didn't vanish. When all those protons and neutrons packed themselves together to form a nucleus, a tiny little bit of their mass was converted into a huge amount of energy.
And that energy has a name: binding energy. You can think of it like a cosmic superglue. It's the force that overcomes the natural repulsion of all those positive protons trying to fly apart, and it's what holds the entire nucleus together. So that missing mass, that's the price of stability. It's the energy that was released, and it's exactly how much energy you'd need to put back in to break the nucleus apart again.
So let's follow that thought. If forming a nucleus releases all this binding energy, it stands to reason that we could release even more of it by rearranging nuclei. And that right there, that's the entire principle behind nuclear energy. And it turns out there are two main ways to do it.
I want you to picture nuclear stability kind of like a landscape. Down in the middle, there's this deep, cozy valley of stability. That's where you find elements like iron. They're the most tightly bound, the most stable nuclei in the universe. But on either side of this valley, you have these high hills of very light elements and these towering mountains of very heavy elements. And both of those, they're much less stable. Now, just like a ball wants to roll downhill, everything in nature wants to move to a more stable, lower energy state. This gives us two clear paths down into that valley of stability. The big, heavy nuclei up in the mountains can split apart to get there. That's a process called fission. And the tiny, light nuclei from the hills can combine together. That's fusion. Either way, they're moving closer to that stable middle, and in both cases, they release a tremendous amount of energy in the process.
So, fission. That's what happens when you take a really heavy, unstable nucleus, like uranium, and you hit it just right, causing it to split into two smaller, more stable pieces. That difference in binding energy gets released, and that's the energy that powers everything from our nuclear power plants to, well, atomic weapons.
Fusion, on the other hand, is basically the opposite. It's when you take really light nuclei, like those isotopes of hydrogen we talked about, and under incredible heat and pressure, you literally squeeze them together to form a single, heavier nucleus, like helium. This process actually releases even more energy than fission, and it's the very engine that powers our sun and every other star in the sky. And let's be clear, the amount of energy we're talking about here is just staggering. Pound for pound, a nuclear reaction, whether it's fission or fusion, releases about 1,000,000 times more energy than a chemical reaction, like burning coal or gasoline. I mean, that is the incredible power that's locked away inside E equals mc squared.
So in the end, our missing mass wasn't missing at all, was it? It was just transformed into the very energy that binds the entire universe together. We basically found the fire of the sun locked away inside a single particle. And I think the real question for us is no longer what it is, but what we, as a species, are going to do with it.